Hey, everybody. I'd like to welcome you to the official Soul workshop with the creators of Soul, Jules Storer, who, of course, is the creator of Juice, and Cesare Ferrari. He's got the best last name in the world. And they're going to give us a masterclass on how to build a simple synthesizer using Soul. So before we get started, why don't we just talk a little bit about why are we using Soul in the first place? So what makes it, what are the advantages of trying to use this to build our synthesizer versus C++ as we would normally do?
Well, it's a lot easier. We announced did an announcement at AEC 2018 where we laid out all the great reasons to use Soul. The main bits about it are, in the long run, it'll give us better performance on more interesting hardware than C++ will. And in the short term, it cuts out the ability to do anything stupid, which is kind of a stumbling block for a lot of C++ learners and experts too, because I make a lot of stupid mistakes as well, and I've been doing this a long time. So with Soul, it's this kind of sweet spot where the language stops you doing race conditions, memory allocations, all the bad things that you have hours of footage on your channel telling people not to do. But at the same time, it doesn't stop the performance side of things. And we've tried to make it as familiar as possible for people who have used anything like C++ or Java or JavaScript or all the other things that look like that before. Soul kind of looks the same. It just doesn't let you do some of the dangerous stuff.
Okay.
If you're a beginner, Soul will be much easier to get you started because, rather than crashing your program, you'll get a syntax error. And if you're an expert, in the long run, we want Soul to be running on really interesting embedded platforms. We want it's going to have latency advantages when we can move Soul programs and have them running on external devices. And I mean, this is a huge topic. We could do an hour about that.
Wow.
But it's got a lot going for it, we think, in terms of the architecture of the language.
Amazing. So where should we start, Cesare?
Right. Well, we gave a talk at the Programmable Audio workshop in Lyon in December last year, and I think we're just going to work through that material.
Okay.
Which hopefully will turn out to be just over an hour or something like that.
We also did a workshop at AEC, which we failed to record. We've done this a few times. Finally, hopefully the camera is actually going to be running for this one.
And the batteries don't run out just at the wrong moment.
People keep asking us, like, oh, can we watch a tutorial? Okay, this time we're going to do it. So, this is the kind of more or less going to be the talk we gave at PAW, which is why it says PAW on the slide at the top. But don't be confused.
Yeah.
Okay.
So the material we're going through is available on GitHub. There's a link at the bottom. So in Solang, there's a PAW 2019 project.
Okay.
I think it's a project. Let's go through this. So I think we've just covered what Soul is.
Yeah.
in a very vague way.
In a very vague way, yes. What we were wanting to do was in this tutorial is get people actually writing some Soul. Now, as this was a live coding workshop, people were able to follow along by actually downloading the tools, and people listening to this will be able to do the same. So there's a curl command here to pull down the latest version. I don't think we can work out quickly how to make curl pull down what is the latest version when you actually do this, but this is this is being recorded, the latest version. If you go to GitHub, you into the releases latest directory, it'll show you what is the current latest version.
Yeah.
So this is for OS 10. This is how you pull down the binaries for OS 10. There's Linux release and a Windows release there, which are available if you go to the releases directory.
Great.
Linux, we've got ARM 32 and 64, and also an x64 build. If you went there, pull that down, and unzip the binaries, you'll end up with some stuff in your directory, and there's an alias here for the Soul command. Basically, we'll have unpacked the OS 10 x64 Soul binary. So if I switch to a command line, this is basically what that would look like if you followed those commands. The alias has been set up, so if I run Soul now, I get the Soul command. As you can see here, this Soul toolkit version tells you which version we're running. This one is not the 875. This is a slightly older one, 830. So there we are. So
should we talk about how you can run Sol?
Oh yeah,
because this is one
yeah.
way of running some Sol code in the command line tools that you can download. Other ways are on the sol.dev website, where the same code can slap it into a web page, no installation needed, and it'll run using web audio and WebAssembly. And the other way at the moment is you can download Traction Waveform, and the latest versions of Traction Waveform come with Sol patch support, so you can also take the same code and actually have it natively JIT compiled and running in a real DAW, which is a really, if you're getting a bit more advanced, that's kind of probably how you want to do this, because then you can record what's coming out of the code and put it through other meters and do complicated routing with it, and actually get a bit more in depth with what's going on, and also have more control over automation and MIDI in and that sort of stuff. But I think mainly for this, we're going to use the command line, which just opens a Sol patch, runs it using the default audio devices. It's very simple, kind of quick tool to get going.
Might be worth mentioning what a Sol patch is.
A Sol patch is one of my favourite pun names that we've come up with so far. A Sol patch is... Sol itself is quite powerful and quite flexible. You can, but a Sol patch is a kind of a plugin-like way of using Sol that will fit into the kind of workflows that we have with existing VST, AU, AEX kind of plugin architectures. So a Sol patch is a little bundle of files on disk, one of which is a little manifest saying what the patch is. You'll have some Sol code in there. You might have some WAV files or other resource files. You could have some GUI UI files in there as well, and the Traction or the command line tools can load that, JIT compile it, and play it back as if it's a plugin. Is that enough detail? Should we?
So would that so would that be pretty much like a max patch?
Sort of. I mean, yes, yeah. I mean, in the same way, it's not compiled. It's not natively compiled. So you can, for example, if you have a Sol patch open in a track, just like you would use a normal plugin in Waveform, you can have a code editor open in the other screen, and you can be editing that code. You hit save on the Sol file, and Traction will recompile, and it won't stop playing. It'll just recompile the code, and that patch will change on the fly. So in the same way as a max patch or other live coding works, you can do the same kind of interactive tinkering with the code while it's still running.
Yeah.
But it's actually very fast. It's JIT compiled with the same Clang LLVM toolchain that you'd use for C++.
Okay.
So the performance is really good.
Wow. So what you're saying is that, and for people that may not know, Waveform is a DAW made by...
Everybody knows that.
Almost everybody.
But yeah, by Traction. Used to be called Traction. We call the DAW is now Waveform.
So what you're saying is that you could have Waveform open, and that you could have a Sol patch that's doing some sort of processing, and that you could actually have a code editor that on the fly changes the DSP in the plugin itself.
So if you were writing a synth, you could record yourself some MIDI, loop it, have that playing through the synthesizer, and be tinkering around with the synthesizer, listening to the loop MIDI, and record the result and peer at the waveform, and have lots of them going if you want.
Wow.
So
theoretically, just a use case scenario, you could have let's say a guitar distortion that was running as software in a kind of traditional plugin format, and then you could actually take the same code and you could put it onto embedded hardware.
Absolutely, yeah. I mean, we at the demos we've been doing, we've got Sol running on the Bella board, which is a very low latency embedded kind of Raspberry Pi style board with audio I/O, and this thing can do like 4/8 sample latency, so it's basically latency free. But it's the same code will run on it, so you can run the Sol patch on there quite happily.
Wow. So the Sol binary that we're running here, there is a Bella version of it included in the Linux repo, which is very low latency. I think it's 16 sample latency by default.
Yeah. So if you're adventurous, you could be following along with the tutorial on a Bella board if you want.
That's amazing. So this could be a game changer not only for C++ plugin developers, but for embedded audio developers as well.
Yeah,
Big game
yeah.
changer.
I mean, I hope so. That's really what we're going with it.
Yeah.
Yeah, and for security as well. I mean, that's the other big win here is that you can't do anything dangerous in Soul code. So if you're building an embedded box and you want people to be able to run any old plugin on your embedded hardware, you don't want to do that in C++ because people can just put arbitrary code on there and it's a security black hole.
Yeah.
Whereas with Soul, you are safe, so you can safely run code that can't do any harm, which is kind of what you need in order to get to safe embedded systems that can do low latency. You need something like this.
Amazing. Okay.
So let's see some.
Right. So the other aspect of this is if we generally code with VS Code with the that as a code editor, and there are some extensions which allow you to get syntax highlighting for Soul. So again, if you're following this and you want to use VS Code, it's worth following the instructions on there to get that code extension installed. If you're using the web, we can follow these links, and this will show you the various stages that we're going to go through. So basically, we can use the SoulDev playground and run these in the browser. So what we want to do is create a synth. So using the command line tool, we're going to create the most basic synth that comes out the software by default, and then edit it and enhance it.
Okay.
So let's follow this. So basically, first we're going to use a Soul to create a monosynth and see if we can run it. So from here, I've run the Soul command. As you can see, there's a little bit of usage help. And what we're going to do is we're going to run Soul create. We're going to create a monosynth, which is a synth. And put it in the monosynth directory. And in VS Code, you can see there's this new monosynth directory has turned up. And we look at the contents, and as Jules mentioned, there's a small extra file that comes along, which is this Soul patch file, which is this manifest telling you a little bit about what this patch is. Main thing here is it tells you what source code is included. There's Soul code can be, the actual source can be split across Soul files, and there's no dependency order problems. You can put processes and graphs in different files. It'll all resolve into one sort of compilation unit. So you can split things as is convenient for you. The is instrument is just a little flag here which helps the command line tool know, oh, it's a synth, it's going to need MIDI, and hence stick up a keyboard and things like that. So from the command line tool, I'm going to play our newly created patch. A small little window appears, and there's an on-screen keyboard. And MIDI works. So this is the starting point. This is the most simple synthesizer that we could think of writing as just a starting point to show people how to get going. Soul itself is composed of graphs, processes, and namespaces. Namespaces being like C++, a collection of other components, other graphs and processes and namespaces. And in this case, we've got a top-level graph. We can tell this is top level because of this annotation saying it's main. It takes some MIDI messages in, and it outputs a stream of floats. And it uses a built-in library function, this MIDI message parser, and it uses an oscillator here as a voice. The connection section tells you how the plumbing works. So this is connecting inputs to outputs. They have to be the same type. And in this case, the MIDI in from our top-level graph is fed to the parser. The events coming out of the parser are fed to the voice, and the output from the voice is the audio that comes out as a stream of audio. So then we can look at this simple processor. It has got two events that it handles, note on and note off events, and it produces a stream of audio. These little functions here are the handlers for each of the events. So when a note on event is sent into the system, this event handler will be fired. It's a sample accurate system, so it's very performant, and it's sample accurate. So the note on and note off handlers are implemented here, and then this run function is the meat of what this processor does. So the processing model is that every processor has a run loop. Think of it as a thread.
Okay.
So your run function is for each of the processes in the graph is continuously running and is executing, transforming inputs to outputs, and when it is finished doing its bit of work, it moves time forward to the next sample, and that happens with this advance call. So if you look at the run function, there's this infinite loop, and forever it is running around here. It's in this case determining an amplitude based on whether a note is being played or not. This is a very, very simple envelope. And it's incrementing a phase based on the phase increment, which is determined from the note that is being played. And then it's outputting a stream of sine functions, which is why it looks like a sine. So basically a sine wave. If I were to take out the amplitude there and resave it, we might hear some nice... Oh, actually, yes. It never releases. Which is fair enough. But
Let's release
back in. So it's about as simple as it can get, really, as for a synthesizer. It's bad in many ways.
Don't do this at home.
Yes, don't write it like this. As I said, the way that the envelope has been sort of mashed into this processor isn't the right model. The fact it's only a sine wave is quite boring. So I think let's take this and go a little bit further with it. Oh, and also the note on note off handling is terrible. So if I were to play 2 notes and then release, it's not going to return. I mean, it's got no. It's not acting like a sophisticated monosynth. It's a very naive monosynth. So, however, it is up and running. So what we wanted to do was make it more interesting. So the first thing that comes to mind is the fact that the voice is currently just a sine wave. We could do something better than a sine wave.
Let's stop for a second.
Okay.
I just had a quick question.
Yep.
So these events, to me, so I'm just trying to kind of associate this with what I would normally see in C++. This looks like a function to me, but they both have the same name. So
they have different types. It's like an overloaded function.
Okay. So there's the overloaded function. Okay, great.
So the name comes from the input event has these types and is called event in.
Yeah.
And there are these 2 handlers for event in.
Okay, great. Okay, and then run is basically main for people that are. Run is
run. Yeah, it's sort of main.
Okay. But there's multiple of them.
You might build a graph with 100 different processes. They're all connected together with audio flowing through them, and each of these little processes has a run function, and each one is spinning in their own little loop.
Okay.
Forever, and each one goes round and round, and each one has to call every time each one calls advance. It moves time on for that node by 1 sample.
Okay.
Magically, that whole thing will run on 1 thread. Or 2 threads or 3 threads, no matter how many there are. But each individual processor thinks it's just on its own, looping forever, running without anything having to ever interrupt it.
I see. So one question. So if run is a looping function, then what if you just wanted something? So phase. So this is more like a audio callback.
No,
be accurate?
it's not like an audio callback.
Okay.
It's generating audio. It's more like it's the opposite of a callback. It's kind of pushing audio. Each time around your loop, you're probably going to read some samples from your inputs if you have input streams. You might not, but if you do, you'll read some. You might say you're just doing a gate, adding two streams together. You might read one, read two, add them up, push them into your output, and then advance by a sample, and then do that again.
Okay.
But it's active. You're not being called to say, here's a sample. You're saying, give me your samples, push a sample. Okay, I'm done with that sample now.
Okay.
And that's the model.
I see.
I mean, we turn, the compiler turns everything around secretly behind the scenes to make it into a callback, but you write it as a push.
I see.
And all of these different, you can build a graph with any number of these things, and they all kind of magically cooperate.
I see. Okay.
In ways that are so complicated and horrible to describe, but
Well, the thing is that's our problem.
yeah.
So we try and do that right, and then nobody else has to worry about it.
Yeah.
Right. So that's that stage. We've got a basic synth up and running, and then the question is, what can we do with it? So I thought it'd be good fun to add a wave shaper.
Okay.
So let's use a very simple function, and we're going to choose tan h to modify the sine wave and make the output a little bit more exciting and enjoyable.
Okay.
We'll also add a parameter, because obviously the world is full of parameters where people want to be able to tweak how in this case, the altering how severe the wave shaping is, how much of those extra harmonics we see. So we're going to create a wave shaper with a parameter using tan h. So we come back to our sort of working copy of the synth. So what we're going to do is create a new processor called wave shaper. It's going to look very similar to the other one. In fact, it's got a stream of audio coming in. So first what I'll do is I'll write it so that it doesn't really do anything useful whatsoever, but it'll hopefully prove the point. I'm going to create a loop that's just going to so for now that wave shaper is just passing the audio through. We can plumb it into our graph. So if we come back up here, this is our synth, and we connect the output of the voice to audio out directly. What I'm actually going to do is I'm going to add a wave shaper.
Wave slapper, you nearly typed.
And I'm going to so hopefully
That should sound the same.
should sound exactly the same.
Phew.
Okay.
Now I'm going to just break it. What I'm going to do, I know what I'll do. I'll output nothing
Ooh, yuck.
every other sample. Bats and dogs will be able to hear. We can see there's lots of moving to zero. But clearly this is having an effect. So good. I've got my plumbing right. This is on the audio path. So what we're going to do is use the tan-h function here. We're going to transform the input with tan-h, and we'll have some multiplier times the audio in.
Nice.
I'll just make that waveform a little bit more visible. So as we change this parameter here, we get more and less. So I'm resaving this. So we can see some control here, which is giving us moving from the sine more through to something looking a bit squarer. Now clearly we don't want to keep recompiling each time we want to change this. I don't know what should we call it. Drive. This drive parameter. So what we're going to do is we're going to create some we're going to add this parameter as a separate input to the wave shaper. It's going to have a name. It's going to have a minimum value, a maximum value. I don't know. 50 is probably good, and some initial value. I don't know. 1. Really quite good. So that'll be nice. Unfortunately, we're not saying how this value reaches the wave shaper. What we need to do is declare this at the top, and then connect it through.
We have new syntax for that.
We do have new syntax for that, but so the drive parameter goes to the wave shaper's drive control. Now all of a sudden on my synth, I have a parameter.
Wow.
So so there we are.
Okay,
Does that make sense?
Yeah. So just starting to kind of put this together now. So the graph is your overall graph containing processes.
You can have other graphs in the graph.
Okay.
A graph can contain graphs or processors.
Okay.
Processor is kind of the leaf nodes, and graphs are the other nodes.
Okay.
That helps.
So then in this situation, we have graphs that contain a processor, and each process contains a bit of DSP, essentially.
Yep.
Okay. And so you have to declare your drive parameter in the graph, and then you have to declare it again within the processor.
Not anymore. You can actually type input. You can actually have promote one, hoist one up from an internal something that's buried in the graph. You can just declare it. Say, hey, at the top level, I want this one to appear, and it'll come up with all the parameters and stuff attached.
I'm not totally happy with the syntax yet, but we've
got that.
We've got some. We're thinking that way about it. I mean, because clearly it's going to be the case that if you are using a component provided by somebody else and they are over time changing, adding and removing parameters, you want those just to bubble up to the top. Okay. Or you might want to say, actually, I only want this one parameter. So there's going to be work done in that area to remove some boilerplate, because at the moment it's not beautiful, but we understand why.
It's pretty good.
Well, I mean, the duplication isn't great.
Yeah.
And when you're creating a stream, so you've created this, and you've created this with very specific arguments. So how do you know what is there an API where we can see?
This is all documented. We've got some documents about what all these parameters are, but everything that's in the double square brackets is an annotation. So that's not really part of the language. The compiler ignores that. Okay. And where that goes, all the drive and the min and max, they all get sent. They got passed up, and you can have anything in there, names of any kind of names, any kind of values you want. They end up in the host. In this case, the host is loading this patch, and the host gets told, "Hey, this has got some parameters called drive and called name and min and max, and in it." And then it decides how to show this on the screen. So that's not a part of the Soul language.
Okay.
So that's what the kind of double brackets mean. So in different host doors, these might be different, and you might have a host which actually has its own special named parameter in there for something that it does that nothing else does.
I see.
I mean, this is they are just strings. So if I were to sort of change this and type it in wrong, now I have a drive parameter that can only have the value 1. So it would be nice to have better support for warnings if things look a little bit weird. But
I see.
So yes, no, there's my parameter. I mean, there's other stuff here. I think there's a step parameter.
Yeah, there's a skew as well. We've got a skew.
So now it can only take integer values.
Yep.
And there's also an interesting slew rate. So if you think of it in terms of, you can hear a step. It's not smoothed, and we can. If I make this very slow, it becomes really obvious what's going on here. I say, but it doesn't. So which means I've called it the wrong thing.
You called it slew rate rather than skew rate.
No,
is it slew rate?
Yeah. No, skew is for skewing the distribution of the where the points are, and slew is kind of where we introduce a filter on the parameter, so it'll kind of
smooth.
It'll smooth the.
Oh, I
yeah,
see. I see.
Which is probably
and
what,
it's not working, which is absolutely typical,
wrong.
isn't it?
I've probably got the wrong name. But all the names of all these premises are in the.
I've got the wrong
are in
name.
the document.
Oh dear.
Yeah.
That's embarrassing.
Well,
anyway,
we'll look at that later.
We'll look it up.
But,
Yeah.
We'll find that.
And so where's this documentation where you
it's
can?
all on GitHub.
Okay.
GitHub, like on the README at the top, it has like lots of stuff you can follow.
Oh, great.
The language, I think there's a language document which has all of this, all the detail in at the moment.
Yeah. So in that, just to ask, so would that apply to input? So now I have input and I can use all of these different arguments or parameters. Is input like the class and
No, input's not a class. Input at the top of your graph or processor, you declare your graph, and then the first thing you declare are its inputs and outputs.
yeah.
You say whether they're a stream or an event, or just a value,
Mm-hmm.
and you give them a name, and you give them a type.
Yeah.
So you know what kind of type of sample or what kind of event object is going to come in and out,
Mm-hmm.
and then you put these annotations on the end.
Okay.
So-
And
Interesting. So if I were to remove those,
yeah.
how the runtime is going to see this is that there's an input of floats called drive, and it's going to say, I've got a microphone. I can do that.
Mm-hmm.
So if we were to save this, we'd lose
Lose
the
our
parameter, but it's actually being modulated by the microphone. Yeah. So the drive parameter is being the audio in it. It's
quite a funky
unaware.
effect.
It's an interesting effect. Yeah. But so it's. The annotations are being used to modify the intention of the streams, because it's not otherwise going to know. Like it's telling that this is a MIDI stream because it knows about this built-in message.
Yeah.
The fact I've called it MIDI in, it doesn't matter.
Could
I
be
could
called
have
anything.
anything. So it's the runtime. The runtime that we're using here happens to have some capabilities that we're using. Soul itself is totally agnostic to all of this. It doesn't know or care.
it doesn't. It doesn't really know what audio or MIDI are. It's
Yeah.
just processing streams of data, streams of event objects, which may be MIDI-like, or they may be something else. So, so the annotations are how the host that's loading this code knows what to do with it and how it should connect it to the outside world.
Okay.
Yeah. Put ourselves back to something that works, as we were expecting. Okay, so here we are. We've got our synth. It's got a drive parameter. The envelope's still terrible. So I think the next thing, if we go to our stages we were doing, I think we've done that. So I think yes, the next thing to stare at is the envelope, and the fact that the envelope is really not very good at the moment. So let's write a very simple attack release style envelope. So it's fairly traditional. We use a linear rate for the attack and an exponential release. We'll need to remove the existing not particularly good envelope from the oscillator and plumb our new one in. So we're going to put the envelope after the wave shaper. So if you think about it, at the moment, the envelope is in the wrong place. So as the envelope decays, the wave shaper is going to have less effect. I mean, it might be what you want, but it probably isn't what you want. So back to our code. We're going to add an envelope, and it's managed to change this. It's about this point that Jules tells me, "Why don't you have the syntax highlighting, the error reporting turned on?" Because I haven't, and I yes, he keeps
every workshop.
Yes,
Because we do have like a Visual Code plugin, a Visual Studio Code plugin, which will highlight the errors in your code. But Ches doesn't make errors, so he doesn't need that.
well, what happens for me is if I put an error, it actually appears in this window here, as it would do if it's running in a DAW. It'll give you the same. I generally use that because I'm a little old-fashioned about these things, but I'll get there eventually. I will get there. So what we're going to do here is our envelope is going to take the same events that we use for the notes. So we're going to take note on, note off events and use those to trigger the envelope behavior.
Yeah.
So again, I'm just going to copy the input events from our envelope. Get my spacing right, otherwise Jules gets cross. We're also going to have two parameters. If you think about it, we're going to need an attack and a release. So in the same way that we did for the wave shaper, we're going to create two parameters. We'll decide what these mean. I think we'll do the same for the release. We'll add a... Oh, we haven't got any audio coming out, which will probably be useful.
Yeah,
An output.
it's a detail.
What should we call this?
Audio out.
Audio out. Okay, I know it's the R envelope, but let's call it audio out. So I'm going to just... So this run loop here isn't ever writing to anything to the audio out, so what will come out is zeros. So hopefully that now still compiles. Jolly good. We've got these, again, the same issue we had before where we want these extra parameters visible at the top level, so I'll include them here. I'm going to declare an envelope. I'm going to and what's actually going to happen here, if you think about it, is that we want some sort of gain component that's going to take the envelope and the audio stream and multiply one by the other. So we need an additional processor. I think it's very easy to write.
While he's typing this, I should mention that we do have library classes that do a gain and an envelope, and like we have more complicated envelope classes. We're writing this here just to sort of show you how easy it is. So we have multi-stage envelopes. We have a set of gains that can apply fixed, mix things with fixed levels, or levels are modulated by other parameters. So
I've just made a classic mistake, which is to not put them in a loop. What would happen then is run would output one sample, advance, drop off the end of run, and effectively that thread finishes. So it's zeros from then on. That's a good gotcha. That's one I've spent time. So what have we got now? As before, we've got the parameters we've got. That should save. We should get our 2 extra attack and release. There you go, 0 to 100. The envelopes are plumbed through to the parameters are plumbed through to our envelope. But if you remember, if we come back down to the envelope, we need the events. So the events are currently only going to the voice, but I've called it a voice. It's actually an oscillator, really. But let's feed these to the envelope event in. The wave shaper output is going to go to the gain components. The envelope audio out is going to the gain in, and the gain dot audio out is what we're going to hear. Now that should still compile, and it'll hopefully produce absolutely nothing. The reason for that is our envelope is currently only producing zeros as its output. Okay, brilliant. I'll make it a little bit quieter and see if it really is working. Yes, there we go. Okay, so that's a very, very simple envelope for us to fill in. The other thing we'll need to do is take out the existing envelope from our sine oscillator. So really make it a sine oscillator without any envelope. So this stuff here is generating our amplitude. Amplitude is a member, we don't need that, and it will come out of there. If we run that, actually, if I play that, what will happen is we'll get a stuck note. resave it. The reason for that is there's now no envelope. Effectively, the envelope is always output the signal. Okay, so now what we want to do is work out what we're going to do in here. We've got these two events that we care about, a note on and a note off. And what we're really going to be doing is saying we need to be able to increment when we're attacking and also when we're releasing. So we're going to need event handlers for so we'll decide what we're going to do in here. So this is... Oh, hang on a second. I'm talking nonsense. I'm actually... Going to be good. We need to know that there's a note. So now what we need to do here is we want to say, okay, we're currently playing a note. So I'm going to say that we're sort of active in some way. There's some confusion here.
Should this be event in rather?
Oh
than
yes,
release?
it should be. I'm
Just testing you there, John.
I'm bound to have diverged from how I've previously written this. And we're going to have some Boolean which starts. So forever, what are we going to do? Maybe this is before a note is being played, whilst we're not. That makes sense. Waiting for a note to start.
Yeah.
Got our starts and stops back. And that's a good illustration of the fact you can have loops within loops. So you don't just write a single loop within an advanced call. You can write lots of loops. You can have different bits of code that are on or off at different times.
So now, clearly, the gain that we've got, 0 and 1, we want something a little bit more nuanced than that. So let's or envelope value level. Oh, it's level. So whilst we're not, and then we're going to do something like that, because that's actually, although it comes first, it's actually us. The note isn't active, so we're heading down towards 0, and then the note is active. We want to ramp up to our to 1 based on our attack rate. So let's have a go at writing that first. We're going to again output the level. The minimum of and the level plus. Just going to throw in a small ramp to make it come up. And I'm going to set the level to the maximum of some factor for the way back down. Let's see if that.
Nice.
Okay, it's working. It's not these. Clearly, we don't want these numbers in here. We would like something based on these these attack and release values. Now, the problem that's happening here is these attack and release values are actually changing every single sample. I mean, effectively, I could be dragging this all over the place. Maybe we don't want to do that because there's going to be a little bit of maths here.
Yep.
We could use events for this instead of a stream. There's a lot of choices. Don't know what the right one is. It depends on the situation.
It's worth at that point noting the different kinds of streams you can have. For if you're writing a sol patch and you have a parameter, then the host will pick up either a stream like this of just floats, just a continuous stream, or they can use that as a sparse stream, which basically it looks like a stream of floats in the sol code. It feels like you've got a full rate audio stream, but actually what's actually coming in is only like occasional bits of data, so it's much easier for when you have sparsely changing values or events. And if you declare it as an event, you'll get callbacks every time the user moves that. It'll be sample accurate, so you can, but with events you can then do your own ramping if you want to sort of smooth that in your own way internally.
So I'm going to leave it as streams for the moment. We can change it. Rate, ramp, step. I'm going to calculate this. So basically this value here, I want something to map this float between the values 0 and 100 into something meaningful. So we want a linear rate based on, say, a 10-second, to take 10 seconds to reach 1 if it's at 100, and to be basically instantaneous if it's low. So we've got to decide a bit of maths here. The other thing we've got, if you think about it, is when we call advanced, time moves forward by a sample, and we need to know what the sample rate is. Because at the moment, nothing in here has mentioned, in this envelope class, has mentioned the sample rate. There is processor.frequency is, this machine would be 44.1. It'll be as in 44,100. It's the sample rate. There's also a processor dot
period,
which is one over
the sample rate, which is also
so maybe what we want to do is say how many samples should the attack take given the current value. This is just a way of thinking about it. What I'm going to do is I'm going to say it's the processor frequency, if I can type correctly, multiplied by, so this is how many samples it should take, the value of our attack. That would be between 0 and 100. I'm going to reduce it down to 0 to 10. Then the step would be 1 over that. And that's the value we want to use in here.
Don't you mean 1 over attack samples?
Yes. Now this could actually be infinity because our attack value can be 0. So as a nice little hack, there we go. At least one sample. I'll put space either side to keep Jules happy.
I was starting to get a bit sweaty there.
Yeah. And it's telling me I can't type. Yes.
We're quite strict about float and int conversions and narrowing of values.
So processor.frequency is actually a float 64, not a float 32. Float and float 32 are, I say synonyms.
Sort of
they're not really. It's really dependent on the platform you're running on. So we're using float, and on this machine, float 32 is the preferred floating point type.
Okay.
You can imagine a future where, in the same way that int might be 32 or 64 on different platforms, float could be 64 or 16 maybe. I mean, who knows? It still builds. This is good. There we go. So that's
slow.
It seems very slow.
Well, it's up to 10 seconds. That's about right.
Is that right?
Yeah. I think you got the maths right.
Good. Right. I'm going to do something similar for the release. Now, instead of this calculation to do a linear step. I mean, I think the number of samples we want might be the same. So in other words, let's go up to 10 seconds for our release.
Mm-hmm.
And it's the same calculation. But release, not attack, because that can be confusing otherwise. And
I have a question.
okay,
Why do you call it processor.frequency rather than processor.sample rate?
What's a sample? We could have done that.
Yeah.
I think we thought about it.
one of the difficulties is that different processors can be running at different rates. Sample rate sort of feels like there is a sample rate.
Mm-hmm.
Okay.
You can over and undersample processors within the graph, so it is a per processor specific property.
Okay.
It's a good question. If it confuses people, we could always add it as a synonym. I mean, we went with frequency. It sounds a bit more, I don't know, a bit more grown up. And we have frequency. Well, we have period as well. So we have frequency and period, which is kind of a bit more physics in naming. If we had sample rate and period, you could have sample rate and length of one sample in seconds would be what a period is.
Mm-hmm.
We've spent a lot of arguments
These
over
are
names.
the sorts of things that happen down the pub. So why did we? Well, it'd be nice to think that in years to come, people say that was a really good decision. But of course, there's also a possibility people say the opposite. Anyway, right. So let's come up with a multiplier here. Now, this is the sort of stuff that I remember very, very badly. How to convert one into the other. So I've got a little crib sheet here, which I think is going to tell me that I need to do something like this. I believe that power function will give me something useful if I can type.
So it's your implicits again. You need the cast to float because you've got a 0.
Of course I have. Yep. Oh no,
it's your 0.001. It needs an F1.
It does indeed.
Okay.
Gosh.
Interesting thing we could do here, I was just looking at the code, it might be quite a fun illustration, is you could move the release samples values, variables out of that scope, put it outside the while loop. And that would mean that it would only update your changes on you're pulling the parameters around it every time it finishes or starts a note. So it wouldn't be doing that calculation every sample.
Yeah.
It would be doing it every time a note starts or stops.
Okay.
Yes, because there's some cost here.
But
this
it's quite
doesn't
nice
mean
to be
that
able
we
to,
can.
yeah. You would still get the same effect. Well, you wouldn't hear it changing as you do it.
Yes, that's
But
meaning.
you'd say, but it's quite nice. One of the nice things we found about this kind of infinite loop style push coding rather than pull coding, like callback coding, is that you can change the scope of something and actually change. Just moving a bit of code up or down actually changes the behavior in a really interesting way, in some quite powerful ways. Whereas if you were trying to do the same effect in a callback, you'd end up having to like write if statements and have little member variables to remember where you're up to, and kind of it like using local variables and scope is quite. You can do some really quite powerful things with them.
So I think what Jules is saying is we could do things like if we pull that up here, for example. What would happen is that the release multiplier would be latched when the note is first releasing, and then we could, if we alter the parameter, it's not going to notice the change of the parameter. But this calculation is happening outside that loop, so it's more efficient. There's different trade-offs. That doesn't feel natural to me. I don't think I'd like it to do that. So if I did want to do that, what I can instead do is use this event mechanism. So what I could do is, rather than having these as being streams, I could have these as events. And as before, I could have, say, the attack. Oops, can't type. Move this logic into here. So basically it's saying I'm going to update the release multiplier, which is going to become a state member.
Mm-hmm.
So when release changes, the event handler is triggered. It recalculates the release multiplier, and then it can use it within this loop.
Mm-hmm.
This feels, I think, better to me.
Mm-hmm. It's certainly more efficient. And it's also a good time to note the two types of variables we have. You can have, like, these ones now are, we call them state variables because they're always there. Any function within the processor can refer to these things, can set, read and set them. They're kind of like a global variable or a member variable, in that for that processor, that instance of the processor, those are part of its state.
Mm-hmm.
And
then there are local variables, which, just like any other language, you have local variables.
So
we call them state because they're not quite members and they're not quite globals.
Mm-hmm. So this now will not compile because I haven't changed the top level events to being the streams at the moment. So I think we will get some. It's actually complaining about something else. It's telling me, but yeah, I've moved the logic and I haven't changed. That should be called attack, and that should be called release. And now it's telling me I've got a stream trying to connect it to an event, and that doesn't make sense. The top level here, I change these also to be events.
There we go.
Hopefully that's back and operational. Yeah. So now we've got that potentially complex calculation being happened only when the parameter changes. So that's more efficient. So that is a very, very basic monosynth.
Okay. I have another question. Well, I have two questions. So you said run is a loop, but then you have the forever loop that's inside run.
Yeah.
So what's the difference between the run, which is a loop in itself?
No, run is the function.
No.
Okay, so run is a function, but
You're expected to have a loop in your run function.
you're expected to have a loop.
If you just write an empty run function,
Yeah.
the compiler's going to say, "Nah, you've got to call advance in there."
Okay.
Well, actually, you could just call advance and quit,
Okay.
and that would just emit 1, 0, and then do nothing. Maybe actually pull up the.
So the other thing I'd say is if you write if you think about it, what run is doing is it's transforming streams into other streams or outputting streams.
Okay.
If you have a processor that doesn't have any streams, you can omit the run function and only have event handlers.
Okay.
So it's really the entry point for the sample by sample behavior of the processor.
I see.
Yeah. If you look at the classic ringtone example now, the latest version of it, it's actually just it's quite a good example of it's a run loop that isn't infinite. The run just plays some notes and then stops, and it's kind of, you write it just declaratively, like one note, play a note, play a note, play a note, and
does it appear in here?
It'll be in there somewhere.
Not been updated.
Not been updated. By the time you watch this video, this will have that will be a lovely little function that just has a loop of pitches to play, and it just calls play note, play note, play note, play notes, and each one just plays a note, plays a next note, and that's something that would be really difficult to write in a callback based style.
Yeah.
I'm just pasting our code into the website.
Nice.
Yep, that's our example. The website has a nice little thing allowing you to show the graph that's going on behind the scenes. So this is a view of the graph. The command line tool allows you to output this as well. It's just not as pretty. Now, you can ask me, when can I edit this and plumb it all together by hand? Yes.
Yeah,
Yes.
one day soon.
Yes.
Ish.
That's
Definitely. I'm looking forward to writing that.
Yeah. And it comes back to that idea about what's the advantage of Soul versus traditional development is tooling, but we don't have it yet.
Yeah.
So really we're building the groundwork that allows some really lovely tooling here. And I think to be as an entry point into DSP, if you had a library of beautiful pre-existing wave shapers and envelopes and things, and you compose those existing components and plumb your parameters through and build synths at high performance and run across platforms and embedded stuff, I think that's very compelling.
Yeah.
And the moment you start double clicking on that envelope and seeing the source code, it's then a very easy route into the world of DSP development, as in programming, rather than kind of sound design or patch creation.
Yeah. Yeah, this is really interesting here. And it makes it very easy to see where the parameters are.
Yeah.
Yeah.
These can get pretty complex, these
Yeah.
graphs. So, I mean, that was a really, really simple and manually written synth example. If you go to the website, we've got examples of like much more complicated synths that use more library functions. So they kind of, they'll have we have voice allocator library classes, and the enveloping. The envelopes are in library classes now, but we have like examples of how those are put together to make some really quite complicated synths.
Right. Yes. So then we were talking about other things that are interesting here. Yes, the slew rate stuff. I don't know why the slew rate didn't work before. I've got a feeling. I'll try it again on the website. It may be that it's not on the command line tool. Can't remember. No. As I said, it's to do with the runtime environment. Which of these parameters are interpreted and understood? Aliasing is an interesting one. That the wave shaper is very aggressive and will produce massive number of harmonics. So if we come back here, back to our view editor.
I think you're playing on the other.
I'm playing on the
other one.
Yeah, I just used it on the screen keyboard. Nope. Oh, hit compile. I know. Bug. Yes. If you recompile, the parameters get lost sometimes. It's a feature. So if we see this with the drive set low, we can see that there's not many harmonics here. If I whack the drive up to maximum, we start seeing aliases. So, as is very typical of wave shapers, that this is a problem for them. I mentioned before that processors don't all have to run at the same sample rate. The way we do that in Soul is this declaration of a wave shaper. I can put a multiplier on with an oversampling factor. So this will simply insert the wave shaper into the graph with up and down sampling either side of it to hopefully reduce those aliases. So this is as it was before. We can see big harmonics. I compile that version. I'm feeling I'm going to have to put the slider up high again. Oh, look, there we go. Alias is gone. So it's quite easy to experiment with things like that, and because we can do individual processors, you've got a lot of flexibility to tune exactly where the oversampling needs to be done.
Wow.
So yeah, that is our very, very simple monosynth. Now the actual behavior for note on note offs is still very naive. So as I said, if you play multiple notes and release them, you'd expect maybe the pitch to move back to the still held notes and things like that. There's a load of things you could do, which is one of those areas to explore. I don't think we've got those components in the library to allow you to do the sophisticated.
The voice allocator might do that. I can't remember.
No, I think we've got a polyphonic voice allocator.
Yeah, we've got polyphonic. Yeah.
Now,
I have two more questions.
Yep, go for it.
What's the difference between a stream and an event? So you have a stream, which is this continuous set of floating point numbers. So an event meaning that you're waiting.
They're both streams.
Okay.
These are all streams in the sense that they're a continuous flow of things coming in. What we're calling a stream is the thing like an audio stream where you have a sample a number per sample. But if you're only having occasional objects coming in, which could be floats or they could be big structures with lots of complicated things in, like a MIDI event or we have a whole set of note event classes inside. Those are like time-stamped things that come in, but they're all in sync. Imagine audio streams, event streams, parameter streams, all these things are all just a big bunch of parallel streams coming in. It's just they have kind of different qualities. Some are occasional objects at particular times, and some are just continuous streams of data, and others may be running at different rates. And
so is an event like a listener then?
It's a good. I think it's a good way of thinking about it.
Yeah.
The key thing is that you could add 1 billion events, and there's no overhead unless you
Do
actually
something.
fire them.
Yeah. Okay.
So it's really turns into that calling into that function. Streams. There's obviously the more streams you have, there is overhead because there is real data. Every single sample is a value for the stream. Events are discrete in time.
But we also have sparse streams. So if you have streams where you do want it to be continuous, but you're only expecting it to be bursty, or just linearly interpolating between things. So parameters are a good example. Then we do that in order to keep the data rate low. Because the idea is that this should scale up to like thousands of parameters, but we don't want to have thousands of streams of every sample going the whole time, because that won't work. So you have sparse streams, you have events that are a way of thinning down the data that can be thinned down. But where the code you're writing in Soul kind of looks the same. You can't tell a sparse stream from a real stream, even though the numbers you're getting from it have been kind of interpolated and they've not been sent.
I see.
So I can declare a namespace with a struct in it with whatever data I want. I create an event handling that and passing those around so I can have complex data. I can generate events internally. My event handlers can generate events.
Okay.
A good example of that is what we do with MIDI, because we kind of try to leave MIDI we leave MIDI at the door, as far away as we can from the code you're writing. So we have in the example here, we use the MIDI an MPE parser class, which gets events coming in, and those events are just an integer, which is a raw MIDI numbers. But the MPE parser spits out a different set of events, which are note on events, note off events, note pitch change events, and some other classes of object. And then in your code, you can handle those individually as different types of events. So you'll get a note on object, which has a float for the pitch and a float for the pressure. And the actual raw MIDI numbers are long gone. And it's been split up into new types, and then you could generate other types from that. You might want to turn your note on event into something that's specific to your app as a structure, and pass that around.
Okay. I have another question. So the need to cast some of your numbers as some of your parameters as floats, or is that something that you plan on doing away with? Because no,
it's all the rage now. Look at all the modern all the modern languages, all your Rust people, and all the trendy new languages. It's all strict about typecasting. And like when certainly like in C++ for ages, we've had all the compiler flags on full about warning us when we do narrowing conversions, because when you're new to it and you kind of you type in like a double and you kind of try to use it as a float, and the compiler goes, oh no, it's kind of annoying. But when you're a bit more experienced and you've seen a lot of bugs that way, you kind of come to realize that actually you just do it properly. So we thought, we're going to go strict from day one, and it seems to be working out well for all the other modern languages that do that.
Okay. So it sounds like anybody that's really planning on using this really
it's not a big deal. I mean, it's no different to using C++ with the warning flags up in terms of what you can and can't do.
There's so many things we haven't touched on. There's so much.
So much.
The sort of things that I was kind of expecting you to ask is, well, let's say I've written this generic gain component. What happens if I don't want to take floats? Maybe I want float 64 or some other type. Well, we have parameterized processes, so it would basically, you declare a type.
Okay.
and then you use it within here, or there's a lot of other ways of making things more reusable, and that's kind of the intention here. So if you take away some of those type safety questions about casts and things, then if you were someone who was to instantiate a processor you've written in their own context, you'd like them to get told, oh, hang on, that's the wrong type, or I can convert that to that, but I'll lose some precision. Is that really what you want? You want those sorts of warnings. So there are warnings out the system as well as compile errors. Trying to think of a really good example. We've only got a few at the moment.
We only have one warning at the moment.
Is it only one?
It's a performance warning.
Oh, that's true, yes. Okay. Yes, that's to do with arrays, which we've not got anywhere near.
No, we're not.
We haven't touched an array.
I
mean, the other thing that's kind of interesting here is there's no memory allocation in this as it stands, in the sense of dynamic allocation. And so there's a lot of things that you can do which are which some of the restrictions of the language that feel as a C++ developer unnatural and feel like they're going to be overly restrictive. But once you start thinking these things through, you find that it's much better to know up front how many voices do I need, how many notes can be played at the same time, rather than saying I'm going to keep it all flexible and open and have open-ended behavior. The moment that you start thinking that way about it, you'll find that it's actually quite useful. It does mean you have to make decisions about what happens when limits are hit, what happens when the 9th note is played if I've got an 8-voice polyphonic instrument. But I think that's a sort of powerful and useful thing.
But what you might do as a C++ programmer, if you in that situation, you think, oh, well, if they press a 9th note, I'm just gonna do a heap allocation. It'll be fine.
It'll be fine,
and it's not fine.
Well, it is fine a lot of the time.
It's fine 99% of the time
until it's not fine.
And what we have the flexibility to do here, though, is say I'm playing my soul patch synth, and I've got my polyphony set to 8. And I find my 9th notes are, I'm using all 10 fingers, and I want that 9th note. I can add to that soul patch a parameter which changes it to 10 or 9 or 10 or some other number, but which actually it's not. You can't change it dynamically. You'll change it, and you'll have a second pause while the compiler rejits and recompiles your code with a new constant in there for the number of voices, and then it's going to use a bit more CPU now because you've got a little bit more stuff going
overhead,
on. A bit more. The matrix is a little bit bigger, but I can use I needed my 10, so I'm happy with that. But that doesn't have to be a runtime dynamic change for that for things like that. I mean, polyphony is a really good example of that, where it's like up front how many you're going to need for a song. Why have that a dynamic? Why should that be dynamic at all? You already know your limit, so you might as well compile code that's absolutely optimized for the least number you need, because that's going to go the fastest.
And also the fact that it sidesteps all of those horrid problems, all of those function calls you shouldn't make, methods you shouldn't do. We just are hopefully reducing the surface of problems that you have to cope with, and instead there are these other limitations that you then have to decide how you're going to deal with. But I think it's a good trade-off.
Yeah. Those were all limitations that were there anyway, but at the moment people learn those limitations by watching your channel and watching a whole hour on why you shouldn't do this thing and how not to accidentally do it. Whereas we're just not letting you do that. It can't be done.
I suppose another thing I can do here that we've not mentioned is I can add the bug. I've just added an infinite loop.
I think it might catch that one.
Oh, will it?
Have a go. Yeah. We have only one. Yeah, there should be only one runtime error that's possible, which is an infinite loop.
How do I add one easily? I'm going to. Can I do that?
Yeah, that would work. No, it's still catching it. Sorry.
It's really.
So the only thing you should be able to do that can't be detected before that's bad is an infinite loop, and it's impossible mathematically to detect that. Turing proved that, so we're not going to pretend we're going to fix that one. But that's something that the runtime that's actually playing this will have to kind of detect. Hey, this audio callback's taking too long. and then you'll get a runtime error. But it should be.
How about that?
Have a go.
Oh, it hasn't spotted that one.
So yeah, that one's gone wrong. But
then, hopefully,
it'll probably tank out in a minute. But if we've done our job right, that should be the only thing you can do that can. It won't crash. It'll just sort of everything will block up for a second, depending on what the host is. Yeah, that's going to be stuck for a while.
So that's your hopefully what you're left with. If you think of all of the problems you could have.
Yeah,
we do try and stop you hurting yourself, but that's going to be hard. Yeah. Well, it's impossible.
And other things to mention are that we're obviously running this in the JIT compiler, and then the web has a JIT compiler using WebAssembly. But we're also in the short term, not everyone is going to have a DAW that has a Sol JIT compiler in it for a while. So we'll also have a Sol to C++ generator. So you'll be able to write something. You'll be able to take a patch like this and run the command line tool, and it'll spit out basically some Juice code, which is a VST AU that you then compile, and it is this in C++. And we'll also have like a plugin that can load these things dynamically that you can use in normal hosts. And yeah, lots of different ways to run it.
I thought I'd just mention the sort of where to go next with this. Polyphony would be nice.
Yeah.
This is the same code rewritten, which I can show you it here, rewritten to be polyphonic. So what we had before as the top level monosynth is basically what this voice is. So we've renamed it, but it's got the same parameters, the same inputs, the same outputs. But now that represents one of the possible many voices. And we've basically put a top level graph on which has an array of voices.
Yep.
And it's got a voice allocator. And what happens is, if you look at the plumbing, the parsed MIDI events go to the voice allocator, and the voice allocator's voice events get sent to the array of voices. Because it's been instantiated knowing how many voices there are, in this case 8. It knows that it's got an array of 8 output event handlers which are plumbed one-to-one with the voices. So this ends up basically wrapping the monophonic instruments and producing a polyphonic one.
Yeah.
So if I will run that on the command line, oh no, it's in examples. Then it looks as before. Now, if I were to look at it in the, so that should, so the polyphonic one. If I look at the graph here, we see that graph structure with the sub graph.
Wow.
Fairly visible. The voice allocator's name is a bit chunky.
Yeah.
That's a feature.
Yeah.
But again, here, before we see this array of 8 voices.
Yeah.
So this is a good example just to show you where you go next with that, because clearly polyphony is important. And as we mentioned, the number of voices ends up being effectively hard-coded into this. Now, if I were to say, as Jules said, maybe this could be a dynamic thing, I can imagine this top-level graph allowing you, if I put a space in there, because otherwise Jules will get cross, you could imagine the top-level graph looking a bit like that. And there being some other parameter to the runtime saying how many voices of polyphony I want. That doesn't work at the moment, but we could see it going in that sort of direction.
That's exciting.
Or it might be it's a parameter. It might be an annotation.
It's going to be down to the host, because at some point you've got host code that's loading this Sol code. It's looking at what it's got. You're telling it, hey, build this graph for me. This is the top level, and you're going to look. The host is going to look at that and say, okay, what can I do with this? You might say, oh, look, it's got a thing called int voices. What does that? And decide what to do with that. But yeah, it leaves a lot of having the JIT compiler and being able to just dynamically change this stuff on the fly means that you can do some quite clever things in the hosts eventually when they get more sophisticated.
What would be cool is to have it where you can have the graph dynamically change.
Yeah,
Like
we
a-
can do that.
yeah.
I mean,
Yeah.
that's easy. It's the other way around. Making the graph change the code is harder. But because we have the code, because the code actually is, the architecture of the code is graph based, that we can have tools that move graphs around
Yeah.
and which modify the code,
Yeah.
which you can't do with any other language that doesn't have like these graph objects as part of as a first class citizen in the language itself.
Mm-hmm.
So there's lots of things we need to do. We're very much heading towards something which we believe is complete enough to be useful.
Mm-hmm.
So again, feedback on what we're missing, or
Yep.
what we want to know is, it's great, but how will we do this? Or this is very hard, and we've got a long list of those things. It's all time domain. We haven't got frequency domain in here yet. We've got plans for that. It's we don't feel it's a block for making it useful as it stands to a proportion of people that would want to use this.
Yeah.
So that's the question. Really, is helping us prioritize what are the missing features, and also if anybody thinks this is a terrible idea and there's absolutely no way they could ever use it because of something or other,
Yep.
we want to know that.
And I'm sure KVR will be the place that happens. Let's keep all the negativity on KVR where it belongs, and then
It's all,
do
feedback is great. I need feedback. I need the good and the bad. I need to know everything.
Great feedback would be, hey, I'm a professional plugin developer and I'd love to use this, but I can't because it doesn't do this.
Yeah.
And that's because that's stuff that we maybe can easily fix.
So what about UI?
UI. We've not even talked about UI. Like, okay, I mean, this is.
The other thing I was going to just quickly do is fire it up in waveform.
Oh yeah. So waveform. We've used as a little test bed for one of our first bits of UI. I think it's that we've got it on a reverb, haven't we?
Well, what I've done, I think here, if I go to the plugins, remove all song,
Clear list, and then
if I go to this,
scan for soul patches.
okay, I've put my workshop directory on here. So basically, I've said soul patches are found here. If I run scan there and then click on format, nothing's showing up.
They were in there somewhere.
Are they?
In the middle?
Oh, there they are.
There they are.
So these are the four examples and the monosynth. The one that I was just editing have turned up here. So now if I go into a song and drag a plugin, I can take that polysynth version of it. So there it's working in the plugin, and I think
It's not still running on the command line, is it?
No.
Okay.
The other thing that Jules mentioned, this is actually live coded. So if I was to say change the parameter name, it's recompiled on the fly.
Wow.
So you can be developing your plugin whilst running it in the DAW, whilst playing with the keyboard. It's quite a flexible system. It gives you a lot of things that I think previously had been quite a slow development cycle of build, drop in, try and convince the host that the plugin has been updated or whatever it is. So there's some good stuff there, and there's also talking about GUI stuff. Oh no, I would have just removed the. I haven't got the.
Well, what waveform has, which has been quite fun to experiment with because it fits quite nicely with this, is we've had this. Where's it live? You press that. We have this thing called faceplates, and these were originally put in for a rack for plugin racks. But it means you can, if I click the lock, then I can add. I can build my own GUI in waveform.
Oh wow.
And this gets saved as some XML.
Yeah.
And you can do some really quite complicated stuff in here. We've got one of the examples in the Soul repository has a faceplate. So you have a Soul patch in there. You've got your manifest, your Soul patch file, and some Soul code, and a Traction faceplate XML file. And when Traction sees that patch, it loads it and it loads the faceplate with all the GUI controls, and you can have some images on there. I think you can put SVG and PNGs and stuff in there, and colors and gradients and text. And that's a really simple declarative way of adding a UI to a Sol patch. We also, I think, probably the main way as this goes on, people will build GUIs for Sol patches will be as JavaScript, and we'll have like an embedded Chrome window in the hosts. So you'd be using web technology, you'd be using like React or just HTML, JavaScript, CSS in a window, which is then communicating with the Sol code via the parameters and the event streams in and out. And I think that could work really nicely because that's also completely dynamically loadable. So you could be messing with your GUI in real time, you can messing with your DSP code in real time, and nothing ever gets compiled. So I can ship that patch over to you, and you can load it, and you could also even embed that patch in a project. So at the moment, Traction's loading this from where we've got it on disk, but the Sol code could easily be just squeezed into that project. So I could give you the project, and it's got my synth in it, and you don't have to have that plugin. You just get the sound
cross-platform, and supported
platform.
on platforms that didn't even exist when the patch was originally written.
Wow.
With even the GUI in there. And I think what we can end up with is you can have say a sound designer is releasing 100 sounds. They might have 100 patches which reuse a lot of the same GUI, but maybe they're slightly different in different patches for different uses, and they could reuse a lot of the same synthesis bits and bobs behind the scenes, but each one kind of looks the same, and each one gets compiled individually when you need it. But you can distribute any one of them individually in it, and it's just a more flexible way of building sounds that just do what that sound needs, rather than being a sound for a fixed plugin. That you have
it
to
definitely blurs that idea between what's a plugin, what's a patch. Is very fluid with this system, with a JET system, and so I think we could see some really interesting ways of using that technology.
And it'll work on the web as well, of course.
Wow.
So ideally, the same patch that you could load in a Chrome embedded thing in a door, you could run that in the website.
Yeah. Live coding as well is.
Yeah.
I think it has a lot of potential for live coding as well.
And I think for you, there's a lot of interest. I mean, I think there'd be a lot of interest in live coding, DSP, workshop type online material, where you can talk somebody through a concept, and there can be an editing window, and they can be altering some Sol code, and it's playing in the browser.
Yeah.
That could be very interesting.
Wow. That's very interesting. So how far do you think we are away from being able to take a Sol patch and put it with like a React UI? Are we thinking years, months?
I think if we don't get that project started this year, then we'll be a bit far behind, because we really need to see some exciting stuff. But we can do it in parallel to all of the DSP stuff we're doing. So, it's top of our priority list.
Nice.
We have this thing that we're trying to make sure there aren't any gotchas in what we've done. That it is a good idea, because there's so many parallel streams that can be taken forward. Things like that. Until we get some of the processing model right, so the way that the code would interact with the DSP, we've got a lot of ideas there, and we're still tweaking and fiddling. When we get that absolutely nailed down, then we'll be able to provide a stable API for that interface. We need so it's waiting on us to convince ourselves that we've done some other things right.
Nice.
But that's that's good.
That's great. Wow. Well, that's amazing. A lot of extendability, I think, for audio developers.
Okay.
Yeah, great.
No
cool.
more questions. We've answered all Josh's
I know.
questions.
I'm stumped.
We stumped him.
Yeah, I've got loads more questions, but it's probably best if I just actually go into Sol and
go have a go. If people have questions, then they know where to find us.
Yeah, absolutely.
And we're more than happy to chat.
Yeah, leave a comment in the comments below, or also on the Discord. We have a dedicated soul room where Cesare has been in there every now and then, and people have been experimenting. So be sure to ask questions and complain if you feel I'm looking forward to seeing what people create with this.
Yeah, us too. It's gonna be
great. Well, thanks again for your
thank
all
you
your
so
time.
much for having us on. Hopefully we've actually recorded this.
I
one
know.
and people will actually get to finally see a tutorial.
Yeah. See you again soon.
All right, cheers. Perfect.